Hello everyone, welcome to this deep dive into naive-Bayes classifier, one of the most important and widely used machine learning algorithms for classification. Today we'll explore what naive-Bayes is and why it is called naive, the mathematical foundation Bayes theorem, and how naive-Bayes uses it. What is naive-Bayes? At its core, naive-Bayes is a probabilistic classifier algorithm based on Bayes theorem. It is called naive because it assumes that every feature in your data is independent of all the other features given the class name. Why is this assumption naive? Because in real-world data, features often interact with each other. But surprisingly, despite this simplification, naive Bayes works very well in many applications like spam filtering, sentiment analysis, and medical diagnosis. Now let's look into the foundation of naive Bayes, the Bayes theorem. Bayes theorem provides a way to update our belief about an event based on new evidence. The formula for Bayes theorem is probability of A given B is equal to probability of B given A into probability of A by probability of B. We call probability of A given B as posterior probability. We call probability of B given A as likelihood. Probability of A as which is the prior probability of A, and probability of B or the prior probability of B as the evidence. Now let's apply Bayes theorem to classification. For suppose, assume we have by which is equal to a class label like spam or not spam. And we have features x which is equal to x1, x2, x3, representing the number of features. Now we want to calculate the probability of a class y given the features x. We do this by implementing the Bayes theorem in the following way. Probability of y given x is equal to probability of x given y into probability of y by whole by probability of x. So probability of class given features x is equals to the probability of features x give, given each class into the probability of each class by probability of each feature x. So the main theory of naive Bayes is that it assumes all features are conditionally independent for a given class. We can say that probability of feature x given class y is equals to the product of probabilities of all xi's or data points xi from the feature x given class y from I is equals to 1 to n. Now, generalizing this, we can say that y cap or y predicted is equals to the maximum probability we get for each y label or class label y, where the probability is equals to py into probability of x given y, where x is the set of all features, which can be written as the product of all xi given y from I is equals to 1 to n. Now let's look at a practical example. Here we have a data table with features outlook, temperature, humidity, and wind, and label play golf, where play golf has two values, yes or no, which represent if you can play golf for that set of features or not. Sunny, here we look outlook has three values, sunny, overcast, and rain. Temperature has three values, hot, mild, and cold. Humidity has two values, high and normal. Wind has two values, weak and strong. And we have a set of 8 data points. So total samples is equals to 8. And in the samples, the number of yes is equals to 4 and number of no is equals to 4. So probability of yes is equals to 0.5 and probability of no is equals to 0.5, which is, now let's calculate the likelihoods, which is probability of xi given y. We use Laplace smoothing to avoid zero probabilities. So the formula for probability of xi given y using Laplace smoothing is P of xi of y is equals to count of xi in class y plus 1 by total instances in class y plus number of possible values of xi. So the possible values for the future outlook is three values. The possible values for the future temperature is three values. For the possible values for humidity is two values, and possible values for wind is also two values. In this formula, if we calculate the likelihood of each combination, we get the following data. Using these likelihoods, if we want to predict for a new sample, for example, outlook is equals to sunny, temperature is equals to cool, and humidity is equals to high, and wind is equals to strong. For a day like this, if you want to predict if we can play golf or not, then y predicted or y hat will be equal to max of probability of yes dash x, comma, probability of no dash x, where this is our x. So probability of yes dash x will be equal to P of yes into P of sunny yes into P of temp cool yes into P of high humidity and yes into P of strong winds and yes. If we calculate this using the likelihood values and the value of probability of yes, we get the probability as 0.0068. Now, in the same way, the probability of not playing golf, given the features x, will be equal to 0.0363 after calculation. Now, if we check the probability of no given the features x is greater than probability of yes given x. Therefore, our y hat will be equal to the max value, which is equal to no. So this is how naive Bayes works on a general scale. All the algorithms of naive Bayes does the same thing on a larger scale to find the predictions. To look into the pros and cons of naive Bayes, we can say that the pros is that it is easy to build and fast train and works well for large feature sets and handles both continuous and discrete data with the right variant. But the cons are the independence assumption is unrealistic in many cases. Sometimes it gives poor probability estimates and struggles with correlated features. Let's look into a Python implementation of naive Bayes from scratch. Now, this is the Python code which implements a naive Bayes classifier from scratch. First, we import the required libraries like the mat, numpy, and default it from the collections. This function does is that it groups the data points by the class X is the list of the future vectors and Y is the list of the corresponding class labels. Zip X comma Y pairs each vector with its label. The separated is a dictionary where each class label maps to a list of its future vectors. As a whole, this function returns the data points grouped by the class labels. The next function, the Gaussian probability, is used to calculate the PDF for a given X value and the given mean and standard deviation. This function also handles the edge cases where the standard deviation is 0, meaning all training samples had the same value, where it returns 1 if the test value matches to the mean exactly, and 0 if it doesn't, or when there's an impossible event. Then it calculates the exponent part of the Gaussian PDF formula and returns the full probability density for a data point X. The next function calculates the prior probabilities for each class. It initializes a dictionary to count the occurrences and counts how many times each class appears in Y. Then converts the counts into probabilities by dividing them by the total number of samples and returns priors as probabilities. The next function, calculate class probabilities, calculates the posterior probability for each class. It first initializes an empty dictionary to store the probabilities by class. For each class, it starts with the prior probability of the class. For every future, calculates the likelihood of the future value in the input vector under the Gaussian distribution defined by the class's mean standard deviation and multiplies all likelihood with prior to get the total probability, and store this product in the probabilities dictionary for the class. At last, it returns all the computed posterior probabilities for the input vector. The next function, predict, calls the function to compute the posterior probabilities and selects the class with the maximum probability and returns the predicted class. In the next section of the code, we define the inputs X-train and Y-train. After defining our inputs, we feed these inputs into the summary by class function to compute the mean and standard deviation per class per future. After this, we compute the prior probabilities for each class of the training data. Then we initialize the test variable. Then we use the predict function, which takes in the summaries data, the priors data, and the X-test data, and gives the predicted label. At the end, we get the predicted output from the predict function. Now let's run this code to check the output. So the predicted class, using the given data for the test variable 1.5, 2.4 is A using neighbors. So in this video, we learned what naive Bayes is and what the foundation of naive Bayes, the Bayes theorem, is, and how to predict a given label or an output from a given set of features and its mapping labels. After this, we looked into an example of how naive Bayes works, and at the end, we looked at the practical implementation of naive Bayes from scratch using Python. Thank you.